right. So I'm going to save all the demos for Kelsey, but what I'm going to do here is kind of talk through different pieces of Rocket, and particularly the app container spec and how it all fits together, and what we were thinking when we built it all. All right, so the first piece of Rocket and what we've been building is a thing called the app container. And so before we even started building Rocket, we kind of wrote down the properties of what we wanted this thing to look like. And so what popped out was the spec, which is still an evolving spec. And we owe a lot of gratitude to the people who've been helping us out. And I know those people will be up here. So Toby from Mesosphere and maybe somebody from Pivotal. And so we've kind of evolved this and thought through the things that we thought were important. And there's essentially three major parts to the spec and how this thing all fits together. The first is the images, or how they're in the spec. They're called Akeys, sort of like an AMI, but it's a container image. And so it's an app container image. And essentially, we wanted to use really boring technologies as much as possible. So the Akey itself is the root file system, like all the bits that you actually need to run, and then some metadata, so describing what the container is, what it expects for environment variables, what it expects for isolation of various types, whether that be like what we think of as like C group sort of isolation, like only give me a gigabyte of memory, or networking requirements, those sorts of things. And so it's just a JSON document describing what needs to happen for this thing need to run. And so it's all enclosed in a tarball, and then it's optionally gzipped or compressed with bzip or xz. And the critical piece is that we wanted the whole thing to be addressable via a hash. So the specification actually says what part of the Akey you hash. And the thingy that you hash is the tarball without any compression. So that's hopefully a globally cacheable and addressable object that you can have. And so within Rocket itself, we actually have a content addressable store, something like the Git content addressable store, where we hash and store all these images. And so in addition to that, we also can say that images have dependencies on other images. One of the use cases that we thought this would be really useful in is to say that you're not shipping 1,000 copies of the certificate authorities that you think your application should trust. You say, this depends on our golden certificate authority image. And that gets pulled into the file system before it starts executing. And then after the image format is the actual runtime. And the runtime has a couple of interesting properties to it. The most notable is that the runtime allows for multiple app images to be executing inside of a single container. And we actually monitor those processes and ensure they stay up. So you can set restart policies around the actual processes and say, this process, if it exits with certain status codes or certain signals, make sure they come back up. But if this guy exits, just kill the entire container and just move on. Pretend like that thing's completely dead, even though there might be other executing processes. And then the runtime can apply isolation to the entire container. So I can say this entire container can only have a gigabyte of memory, or this individual process, this individual app can have only a gig of memory. And so you can have these two layers of isolation. And this is a piece of the spec that I think we want a lot of eyeballs on, because this has a lot to do with how we want to extend cryptographic identity from the host down into the processes. So when we think of cryptographic identity, we have that already for our hosts. And in a lot of cases, we rely on the SSH fingerprint, the SSH key of a host, and we trust that. Once we connect to a host once, we trust that we connected again to the same host, because that key gets recorded into our SSH known host file, and it doesn't warn the second time you connect. It's not a great way of doing trust, but it's what we have, and that's what the entire internet runs on. So hopefully it's good enough. We'll find out. But we would like to extend a similar amount of trust down into the container itself. So there's an identity service over HTTP that the app container spec defines, where you can validate a token that you get over the internet from somebody else. So this token is, hey, I'm container XYZ, and I sign this payload, and here's the hash. And is this actually from this container or not, and it returns true or false, 200 in this case because it's over HTTP. And so you can think of it as extending trust from the host level into the application. And then also along with doing this sort of this HMAC process, it allows you to introspect the container and figure out what is in the container. So you can find out the original images that are running in that container. You can find out what the isolation is on that container, et cetera. The next piece is image discovery. So one thing that we wanted to do with the spec was to spread out the container namespace over the currently trusted or currently well understood DNS namespace. So when you get an app container, or you're looking for an app container image, you can actually say use a well-known DNS name. So in this case, this will actually run with the current prototype. So you can say coreos.com/etcd and then colon a version number. And that it will use this discovery process to find where the actual bits, where the actual tarball, the actual compressed tarball of this image exists. And the way it does this is it recurses down. It makes HTTP GET requests beginning at coreos.com/etcd, and it's looking for these meta tags. If you're familiar with HTML, that you can have a head document and a meta tag in there, and it's looking for these meta tags that describe where you can actually find the tarball of this image. And so in this case, the actual app container image for the etcd container is being served out of github.com/releases/ et cetera, et cetera. And so we're just hosting it in the same places that we release our regular etcd release tarballs for Linux. We just have an ACI file on GitHub along with the tarballs. So you can now just distribute the namespace over the existing DNS infrastructure. And since it's a meta tag, it's completely static. You don't have to have a special server serving up this information. And along with the specification, we've written out a few tools to help people sort of navigate the specification and do building of ACIs. So there's a subcommand for the AC tool called build, which takes a root file system and the manifest and builds a proper tarball and validates that the JSON document is correct. There's obviously a validate tool, which you can point at an ACI or a manifest or any number of these things that are in the specification, and it'll return you a 0 or 1 on whether that thing's valid. And then a tool that will do the discovery process, so you can test that the meta tags are there and that the actual ACI files exist. And it will, so you give it a like coreos.com/etcd, and it'll say, oh, all the tarballs for this image are here. And also with the discovery process, you can have other transports like HDFS or BitTorrent or something like that. It's not really specific, but it's just a template for discovering where the actual image is. OK, so Rocket, the command line tool is RKT, because all the best Unix commands are 3 letters, like Vim, not Emacs. No. So Rocket is an implementation of this entire spec up to this point. And so it has a few subcommands. The first is rocket fetch, which you can actually give it a like coreos.com/etcd or an HTTPS URL to the ACI file. And what that will do is it'll download the file, it'll validate the file, it will uncompress the file, it'll hash the file, and then it will store it into the content addressable store at varlib rocket. And so anytime that you ask for that URL again, it will just use the hash that's on disk. And if anyone wants to start sending pull requests, we need to start doing e-tags and cache invalidation there too, based on the HTTP responses. But we haven't implemented that yet. It just does a really dumb, have we seen this URL? Yes, the hash is over here, dereferencing. So we have an index on the URL, and then we also have secondary indexes on the actual name of the app container image. And the idea with Rocket Fetch is that we would like it to operate something like the shared mode in Git. so that you can execute Rocket Fetch as an unprivileged user, download all the bits that you need to run, and then run the actual container as root, because you need to talk to the kernel, et cetera. To set all that up, you need to be executing as root. But we'd like to avoid running the fetches, which are talking over the internet, possibly to attacker servers, to avoid running those as a privileged user on the host. All right. So Rocket Run is the other piece of this. We joked about calling it Rocket Launch, but we thought it was just too far. So this is the actual meat of the process, and so it'll take either URLs or names of the ACI. And one important thing about Rocket Run is that it directly executes the container. So it's not talking to a daemon and then that daemon executing it. So this means that you can use the Rocket command line tool, and it integrates with your existing process management tools or init systems, et cetera. It essentially behaves as like a static binary or any other service, like user bin Apache 2. You can do Rocket Run etcd, and once etcd dies, then the init process is notified, hey, it died, and can take whatever action it needs to do, page you, log it, et cetera. So there's no external daemon. It's executing in that process tree under that C group that it was started under. All right, and this is where the Rocket puns continue. Rocket is divided up into 3 stages. So the first stage is stage 0, which is the actual Rocket binary. So this is user bin Rocket or wherever you decided to install it. It's in charge of downloading the image, pulling it out of the content addressable store, unpacking it on disk, and then actually at that point the stage 0 is done, and it executes stage 1. And stage 1 is currently implemented. What it does is it transforms the JSON manifest of the thing that you want running, and then it executes the inspawn, and it launches PID1, which is a systemd PID1. Inside the container. And so we use systemd just to monitor the processes and do all the restarting and all the forking, et cetera, that Rocket does. But you can imagine other implementations of the stage 1, and we've actually prototyped out another implementation that uses QEMU KVM instead. So you could isolate the entire container inside of a kernel and a little hypervisor too. So the stage 1 is something that we intend to have other implementations of, but the current one is done that way. And then stage 2 is the final stage, which is the actual execution of the app container. So this, in the example we've been using so far, this is the actual etcd process, and it's going to be isolated inside of its own chroot, so it doesn't have access to any of the stage 1 stuff. And then it's an active process of applying the isolators and any of the restart policies in case that process exits, et cetera. And then once the stage 2 completely exits, the entire container is destroyed, like I mentioned, and at that point it can be garbage collected by a garbage collection daemon, and or manually garbage collected. We have a subcommand, Rocket GC, which we've started to write to, that just walks through and locates any containers that have exited in varlib Rocket and just deletes them. Obviously, there could be other policies or other things that people may want to implement, but we'll have a thing where you can say, run that on a timer or something, run that GC process. All right. So that's the full execution flow, discovery flow of an image, and the current state of the prototype and kind of the high level of how that works. And so that's it. So I can answer a couple questions while Kelsey's getting set up here.
Yeah, I think now would be a good time. If, again, questions specifically on the technical front, now would be a great time to ask those if you have that.
Yeah. Yep.
Will you provide a tool to translate from Docker files to your image format?
From Docker, we started writing out the process of converting from like a registry endpoint to the ACI format, but initially, I don't think we'll try to implement the whole Docker build process or something like that. This is just like, I have a Docker registry and I want to try to run it under, or convert it into an app container image. And that'll be the first thing that we build. Yeah.
And do you know if GitHub is okay with hosting all of the local files?
I don't know if they're okay with it, but it could be like AWS S3 or something else too. But I mean, they already are hosting tarballs of release images, but we'll see if we get complaints. Yeah.
Kind of I guess, I don't know if you guys have looked at libcontainer and extending that to also support this, but my question is really around, do you encapsulate all of the platform dependencies into the Akey? So to be able to do things like suspend, live migrate,
So those sorts of things would be the responsibility of like the stage 1 of like a live migration or something, because that's the root, like that's the PID 1 of the process tree. And so if you're going to do a live migration, like with checkpoint restart or something, you have to capture from the PID 1 down. And so that would be the responsibility of that thing. Hopefully the app container just never is aware. That's sort of the goal.
That's very interesting.
Please try to repeat the questions too.
Oh, sorry.
So for logging, do you expect that to be standard error, or what's the deal?
Yeah, so the question was about logging, whether it be standard out or standard error. Right now, it goes to standard out and standard error. And also the specification says if another logging option is detected, say you detect that a journal is in there, you can use that too. Or syslog is in there or whatever. We're not super opinionated about that because again, it's the same process as if you had executed on your host machine. It's executing in that namespace, and there's really, yeah.
So you have the image format is basically a tarball, and you say you can have like chain dependencies and that sort of thing. How do you deal with? Do you presently have a model for like if a dependency needs to overwrite or delete things in other?
Yeah, that's a really great question. So the question was about currently the app container image has a dependency list, and how do those dependency lists override each other? So the dependency list is ordered. So it says it essentially is layered. So it says this thing goes to like Etsy SSL or something, and then this other thing goes to Etsy SSL, and so essentially it's like a copy over it. And so anything that is, and it's ordered, so the list is ordered, so anything that's at the bottom of the list is going to get clobbered by any entries that are above it. And then we also, at the end of the entire dependency chain, you can offer a whitelist of things that should be pruned. So if you need to prune the tree, you have a whitelist of the files that should exist at the end of the app container being exploded onto disk. I'll take one more. Are you almost ready?
I'm ready.
Okay, I'll take one more. Yeah.
Why install and not leave container?
It was mostly just choice. Why inspawn and not libcontainer? So we wanted to use systemd as the PID 1 on this initial prototype because it saved us a lot of time. And inspawn's really good at executing systemd PID 1, and it's just fast to get that working. I could imagine that we also do a stage 1 with libcontainer. It's just wasn't in the critical path. Yeah. All right. I'll hand it over to Kelsey now. So thanks, everyone.